Welcome back to SAT Books, in which an SAT Math perfect scorer and 99th percentile scorer Rifat Bari shows you how to get a perfect score in the reading section. Today we're continuing our discussion of Energy and Civilization, A History by Vaclav Smil, a book which has been recommended by none other than Bill Gates. Today we're doing a deep dive into the next section of E&C, and that section discusses about terminologies discussing energy, power, and work. Let's get right into it. Smil begins the next section by talking about tools. Tools multiply the power under human command. As a matter of fact, they give humans a chance to do much more work than they otherwise could with their bare hands. A classic example of this is boats, which use sails to leverage the power of Mother Nature. So for example, boats will use wind currents and ocean currents to guide them to their journey. But there's a limitation. If the wind never takes you north, you'll never head in that direction. A classic failure of this, or a classic result of this, is when the Spaniards actually crossed the Pacific Ocean multiple times to get to Philippines. But they never once made it to Hawaii. Why? The ocean currents and the winds never took them in that direction. So they never knew about Hawaii. Talking a lot about energy, so it's worth mentioning the first law of thermodynamics, which states that energy is not created or destroyed, only transformed. A classic example of this is that any type of energy can be converted into heat energy, a principle which heat engines use to this very day. Now here's the thing, even though no energy is lost in the conversion process, the potential for useful work decreases during the conversion process from one type of energy into another. The second law of thermodynamics states that entropy always increases in a closed system. As a result, energy conversions result in an increase in entropy. That means disorder increases, the potential for useful work decreases, and the complexity of a system also decreases. The homogeneity of the system increases. However, we have broken the second law of thermodynamics. Not just us, but every single organism that has ever lived. Because every single living organism, has to defy the second law of thermodynamics to survive. And why is that? It's because the metabolism of these organisms have to collect, synthesize, and transform energy in very complicated ways. As a result, energy is stored in a very complex, heterogeneous way that actually decreases entropy instead of increasing it. And so, all living organisms must be open systems, which is why they can decrease the entropy of their system in their bodies. And so, that's how every single living organism defies the second law of thermodynamics, by just being alive. Because their metabolisms collect, synthesize, store, and trap energy in very complex ways that decreases entropy. That's why we say no living organism can maintain a state of thermodynamic equilibrium when it is alive. Why? Because all living things must collect, synthesize, and metabolize energy when they are alive to facilitate their growth, their evolution, and their renewal. As a result, that's why all living things maintain a continual inflow and outflow of matter, so that they can defy the second law of thermodynamics and not maintain a thermodynamic equilibrium when they are alive. Now I want to talk about the diminishing utility of converted energy. That means when you convert energy, its potential for useful work decreases. A classic example is when you're using a table light to read a book. The electromagnetic waves from that light, from that lamp, are hitting the pages of your book and lighting them up so that you can read the words. But it is not so simple. Let's say you have an electric light. An electric light is most likely made by coal. In fact, in 2015, 33% of electricity in the United States was created using coal. Now, this coal-powered electric light is not that efficient. In fact, 60% of the chemical energy contained in that little lump of coal turned into heat during the processing stage. And when the remaining energy is turned into light, well, what happens? A lot of that energy, even though it might strike your page as electromagnetic waves, it heats up the surrounding area near your page, and it turns into the random increased vibrations of molecules in the air. You can't harness that energy anymore. So you went from a highly useful form of energy, the chemical energy contained within that coal, to a very useless energy, the kinetic energy of the molecules vibrating in the air, because they were heated up by the light waves, the heat striking the page. Now, here's the other scenario. Let's say you have an incandescent light. Well, that's even worse. Why? Well, only 5% of the light coming from that filament is actually electromagnetic waves. The other 95% is just heat. That's why when you touch a light bulb, it's so hot. If you're using an incandescent light bulb, 95% of the energy comes out as heat. Only 5% comes out as actual light. That, folks, is a direct application, a direct consequence of the diminishing utility of converted energy. Now let's define some terminology. Energy is typically measured in joules or calories. Next up, the rate of energy flow is power, which can be measured in joules per second, or in industrial applications, horsepower. And finally, energy density is the amount of energy per unit mass of a resource. Now, here's the reality. Low energy density foods never become staples. In fact, the pre-Hispanic inhabitants of the basin of Mexico had an abundant supply of pears. Now, pears, like any fruits, they're not very, energy dense. Pears, their energy density is only 1,700 joules per kilogram. What does that mean? That means a small woman surviving only on carbohydrates, forget about the other two macronutrients, surviving only on carbohydrates, needs to eat 5 kilograms of pears every single day just to survive. Just for her basic metabolic function, she needs to eat 5 kilograms of pears. Who's going to do that? That's not realistic. It's not realistic. On the other hand, she could just eat 600 or 650 grams of ground corn as tortillas or tamales, and that's it. She'd be fed for the day. She'd have enough energy in her body to work or do whatever activity she would need. Now let's talk about units, because a lot of people get mixed up when it comes to units. So let's start off with 1 Newton. How much is 1 Newton? How heavy is it? Well, it turns out it's not actually very heavy. It's just 2 Snicker bars. Each one is 50 grams. So 2 Snicker bars would be 100 grams. And if you held 2 Snicker bars, if you put them on your hand, that would be 1 Newton of force acting on your hand. How about 1 joule? How much is 1 joule of energy? 1 joule of energy occurs when you exert a force of 1 Newton over 1 meter. So for example, let's say I have 2 Snicker bars and I raise them by 1 meter. I will have done 1 joule of work. How much is 1 meter? It's about 3.28 feet. And 1 feet is roughly the size of your arm length. So, hopefully that gives you an idea of how big or how heavy 1 Newton of force is and how much work 1 joule is. What about calorie? 1 calorie is the amount of heat required to increase the temperature of 1 cubic meter of water by 1 degree Celsius. Maybe this will make it clearer for you. The typical woman needs about 2,000 calories a day to survive. The typical man needs about 2,500 calories a day to survive. That means a typical human needs about 2 to 2.7 mcal to survive each day. You can also write it as 8 to 11 mj or m joules, or 8,000 to 11,000 joules a day. What about power? Power is defined as the rate at which work is done. So it's simply work over time, FD over T. Power has a unit of joules per second or watts. 1 horsepower, which is used in industrial applications to refer to power, 1 horsepower is equal to 750 watts. But how much actually is that? It doesn't really make sense until you understand it, right? So let's get down to the numbers. A typical human needs about 8,000 joules of energy a day to survive, right? For their basic metabolic functions. So if a human consumes 8,000 joules of energy in one day, they're using about 90 watts of power just to consume food. Now your typical light bulb is about 100 watts. What about a toaster? Well, that's about 1,000 watts. A small car? That delivers about 50,000 watts. And a nuclear power facility? That delivers almost 2 gigawatts of power. Now let's talk about power density, which is basically the amount of energy that's either produced or consumed per unit area. It's a very important metric when it comes to deciding whether a new type of energy source is useful or not. Now here's the thing. Let's talk a little bit about food. Not all foods are created equal. Just check out this chart. We have the energy density of each food listed in joules per kilogram. The higher the joules per kilogram, the more energy that kind of food gives you. For example, oils and animal fats are very high energy density. That's why people might eat them to gain more energy. So if you were going on a mountain hiking trip and could take only so much food with you, you'd be making sure to take more of these and less of these. You might be thinking, why is power density so important? Here's why. Cities thousands of years ago, and even poor metropolitan areas today, needed a lot of fuel wood and a lot of charcoal for heating and cooking. And that takes up a lot of energy, a lot of power, right? Here's the thing. The phytomass power density is less than 2% of the power density required to heat and cook items for a small city. And so, cities had to find areas with 30 times their size so that they could chop off trees and get the fuel and burn the fuel for heating and cooking. That's what limited the size of cities back in the old days. I mean, you can only harvest so much wood, right? If you're taking up an area 30 times the size of your city, just for survival, that's a problem. And so that's why power density is so critical. It basically decides the size of cities. And nowadays we have cities like New York that have over 8 million people. This just wouldn't be possible with the technology of thousands of years ago, when we still had to use fuel wood and charcoal to power our basic needs. Back then, you would have needed a huge forest, maybe the size of a whole country, to power a city the size of New York. That's why people didn't grow in cities until the Industrial Revolution. Smil ends the section by talking about the importance of the efficiency of energy conversion, which is given as the ratio of output divided by input. Here's the thing. You can't perfectly convert any type of energy into another. There will always be some kind of loss in the form of heat or some other kind of energy. When you're pushing a book, all your energy doesn't go directly into moving the book. Some of it goes into heat, some of it goes into sound, some of it goes into the kinetic energy of the air vibrating next to the book. And so energy conversion can never be perfectly harnessed. But we can do better. We can make energy conversions more and more and more efficient until they reach their mechanic and thermodynamic limits. And that is our goal for making a better civilization. When we make the maximally efficient energy converters, that is the day we can declare success on energy and civilization. Folks, I want to thank you for watching this episode of SAT Books, in which we discussed crucial ideas regarding power density, energy density, foodstuffs, and more from Energy and Civilization by Vaclav Smil. I hope this pumped up your nonfiction reading skills and gave you some critical ideas about how energy relates to civilization. Thanks for watching this episode, and we'll check you out in the next one.